We're starting. All right, so we're moving on to 13.2 today. We're actually going to talk about line integrals. So basically what we're going to do now is we're going to learn to integrals over arbitrary curves. Right? So we know about integration along like the x-axis or the y-axis. We've been doing that in calculus 1 and 2. But now we're going to be able to integrate over any arbitrary curve, and we're actually going to use their parametrizations to do this. That's why learning how to parameterize is very important. So I think the first one we're going to do is the line integral over a with respect to arclength. Okay, let's do that. So let f be a function then its line integral over the curve, which I'm calling C, with respect to arc length, is given by. So I'm both going to define how it's computed and the notation that we're going to use for it. And here I'm just using 2 variables, but it generalizes to 3 or more variables. But it's d little s. S stands for the arc length, right? That's what ds means. This means with respect to arc length. Okay. And here's how we compute that. It's the integral from a to b of f of x of t, comma y of t, times, I don't want to put a dot because that would mean something else, times arc length. We actually know what arc length is, the ds. This. It's the magnitude of that dt, where r of t is the parametrization of the curve C from t equals e to t equals 1. So this is called the line integral with respect to arc length. Because we're integrating with respect to s, ds we know is magnitude of r prime dt, and so you're kind of just doing a substitution here. But what this actually means is look at the interpretation of something like this. Right, so we know integrals back in Calc 1 and 2, they gave us the area under a curve, right? And this is kind of exactly the same idea. So let's say our f of x, y is in obviously a function in 3 dimensions. So what happens is we have some arbitrary curve around here, right? That goes from one point to another point, and that's called our curve C. Now if you're plugging in any points along here, x, y, and you plug it into this, the output is a z coordinate, so that just goes up to whatever that z coordinate was. Right? This is a function that's going to give you the height, which is the z coordinate. And then it's going to calculate that height along this curve that we parameterize, because our x and y are following that parameterization. And so it's going to calculate the height at any given time. And so you get kind of the area of this wavy fence that's following this curve. And at any given time, at any point x naught, y naught, the height of that fence is given by f of x naught, y naught. So this is basically an integral that's computing the area of this fence. Similar to how you compute the area under a curve, it can compute the area under some arbitrary wavy curve in 3 space. This is the point where t equals a, for example, to t equals b. But we'll talk about things like orientation later. It actually doesn't matter here. But let's actually do an example. Compute the integral along c to x ds. So this might be a problem that you're faced with. Okay, so let's actually do this. How do you guys think we proceed based on the definition?
Let's find RT first.
We need to find the RT. Okay. Which is? What? 1 plus 2t, comma, 2 plus 3t. And this is 0, t goes from 0 to 1. So you start at 1, you need to add 2 to get to 3. You attach t to that. Start at 2, you need to add 3 to get to 5. So it's 2 plus 3, add t to that. Do it 0 to 1. So that's an easy way to parameterize anything. What else do we need for the definition?
R prime t.
So 2. Now we find our prime of t. That's going to be 2, 3. What else do we need? We need the magnitude of our prime of t, which is square root of 2 squared plus 3 squared, which is going to be radical what? 14. 13. What do we need to find next?
Our limits. Our bounds on
We know the limits, 0 to 1. What do we integrate? We integrate f of the parametrization, right? Meaning, I'm going to plug in this for x and this for y in the given function. Here my f of xy is 2x. I need to find my f of x of t comma y of t. So that's just going to be 2 times whatever my x value was, which here is going to be plus 2t. And so this means,
Professor, could you explain again?
what?
So you have
This is the function that's describing what my x coordinate is doing.
okay.
And this is the function that describes what my y coordinate is doing. And this is my function f of x. So I'm going to replace all x's with its parameterization, replace all y's with its parameterization.
Okay.
That ensures I'm running along the right curve because my x values are outputting the same things as the curve is outputting. And so this is the function I'm integrating. And so now you just kind of plug them in. Let's just do 5. So now you integrate. So now we're going to integral of c 2x ds.
Professor,
Yes?
don't you need to also, so for 2x you said 2 times 1 plus t. You don't need to put the y because y is not there, right?
There is no y, it's just 2x. So I'm just substituting the x. Okay, so this is going to be, I'm going to integrate that function, 2 times 1 plus 2t, times the magnitude, radical 13 dt. And how do we do that? How would you do this? I take out the constant. And then now you just integrate both sides. So now you integral of 1 is t, integral of this guy is t squared, between 0 and 1. That gives you 4 radical 13. Yes?
Did we choose t goes from 0 to 1 just for it to be easy?
No, because that's the formula that we have to parameterize straight lines. If you use that formula that we did in class, it's always 0 to 1.
Okay.
Specifically because it's a straight line. The limits I pick depend on my parameterization, not on anything else that's going here. And so this falls in line with the formula. I'm using the x1 plus x2 minus x1 times t, blah, blah, blah formula, and so it's always 0 to 1 for that formula. So another example. I mean, we'll get to applications soon enough, but right now I just wanted to make sure that you actually know how to actually do the raw computation, or what it would involve. So what's the first thing we do? Parameterize. RT is going to be
2 cosine t and 2 sine t.
and what's our parameterization here? How do you know that?
Quarter circle.
It does say quarter circle, but what's the picture that we're looking at? So this is the whole circle. We know it's radius 2. This is the point where we have 2, 0, and we're going to this point, 0, 2. So we only need this. So that's the guy in the first quadrant. So it's 0 to pi over 2. Second thing we do is find our prime. Minus 2 sine t, 2 cosine t. Then we find the magnitude of our prime. It's going to be the square root 4 sine squared t plus 4 cosine squared t. What's that? 2. 4. I'm going to find my new f function, my f of r of t. What's that? 3 times 2 cosine t. So this becomes 6 cosine t. So now we reach the fifth step. So now our integral is going to be from 0 to pi over 2 of our function 6 cosine t times the magnitude of r prime, which is 2 dt. So here's just 12 times integral from 0 to pi over 2 times cosine t. This is 12 times, what's the integral of cosine? What's sine of pi over 2? What's sine of 0? Now, application aside, it's going to be very important, as I said, to just be able to do the computations quickly. And we can worry about why we need to do these computations a bit later, but for now, we need to know this thing in terms of the sum. To compute what was the first thing we do? We find our t, which is of course the parametrization of the curve C. C is the name I'm giving to the curve. The second thing, we find r prime. The third thing, find the magnitude of r prime. Fourth thing, you find f of r of t, meaning you're going to take the coordinates from the function that you parameterize and you're going to plug them into your function here. And then the fifth is to integrate. And this is just going to be the product of This is just going to be the product of this step and that step. Now, in this class, we're going to be doing many different kinds of integrals. There are going to be many different kinds of line integrals, and we're going to do other kinds of integrals, and they are going to all have slightly different definitions, sometimes very different definitions. So it's very important now that we really start to pay attention to detail and pay attention to notation, and we should be able to associate the steps to do a certain computation based on the notation we see. You seeing this should trigger this process in your brain without you thinking about it, right? It's not going to happen now because it's like the first time I'm telling you, but you should be like really hammering the homework to the point where you see this, this is kind of automatic. Right? It's kind of like, you know, if I ask you, oh, what's the derivative of x squared? You immediately know 2x. You kind of don't think about it. That's how you want this process to be. Because there are going to be times where you're going to have to be computing multiple integrals. They're also going to be looking similar, but they're really going to be different. So we're going to do, for example, there's an integral I just told you about, which is the ds. Later on, we're going to do something like d big S. Later on, we're going to do something like d big S with a little vector. Things might look very similar, but it's going to be something that you're going to have to pay attention to and realize what you should be doing when. Okay? So I highly recommend, even if I don't do this all the time, in your notes, like you're going to eventually compile like one page that has all these different types of integrals and the steps to compute the different types of integrals, so you don't actually get confused when you see one, right? We're going to do many different kinds of integrals here. So it's important that you start to learn to think of things in that kind of way. Let's see. Okay, here's something I mentioned last time, but we will do it again. Sometimes the curve C will not be smooth rather piecewise smooth. And I kind of mentioned what this was along last lecture. Okay, so this means, like, for example, your curve can do things like have sharp corners and rapid changes of direction and not have any, so right here, calculus can't really work at these points here, but if you break this up into pieces, calculus can work on each piece. And just as how we can split up intervals back in Calc 1 and Calc 2, where we realized the integral from a to b can be thought of as an integral from a to c plus an integral from c to b, we can do the same thing here with c. So let's say this is our curve c. Right? This whole thing is the curve c. Sometimes what we'll have to do is we'll have to split it up. We'll call this one like C1, then call this C2, then call this C3, then call this C4. And so the integral along C is just going to be the integral along C1 plus the integral along C2 plus the integral along C3 plus the integral along C4. Right? i.e. the integral over C is the sum of the integrals over each of its smooth pieces. Right? So if curve C by itself is smooth, like in the previous two examples, that was the case. You just integrate over curve C, but sometimes you will have to do several kinds of integrals. And each piece would have a different parametrization, which is why it's very important that you're very quick with the parametrization, you're very quick with knowing what to do, how to evaluate certain kinds of integrals. You don't want to really be bogged down by that. I think I have an example here. So here we're going to integrate x squared ds. And here's my C. It's the quarter circle from 1, 0, 2, 0, 1. Followed by the line segment. From 0, 1 to 0, 2. So let's draw a picture here. Sometimes that's going to be useful. So obviously if we have a quarter circle and it's going through these points, it's going to be the unit circle from 0 to radius 1, centered at the origin. So we're going from here, which is 1, 0, all the way up to here, which is 0, 1. And then we're going from here, a straight line up to the point 0, 2. So this is our curve here. It does this, then it does that. Notice this part here is a circle, that part there is a straight line. They have two different parametrizations. They're both smooth on their own, but connecting them creates a sharp corner, so I can't just do it all in one shot. I have to split it up into two curves. So I can call one of these C1, and call the other one C2. Being able to sketch the curve is going to be important later on. I think it helps your intuition a lot. Especially when we're doing something like this in 3 dimensions to really realize what's actually going on. You're probably going to want to know how to sketch it. So when faced with a problem like this, here's what we're going to do. We're going to have C1 and we're going to compute that. We're going to do the integral over C1. So we do and find RT for C1. What's that going to be? T goes from 0 to pi over 2. That's the quarter circle. This means my R prime is minus sine t cosine t. This means my magnitude of R prime is just 1. This means my f is x squared. My x is cosine, so this becomes cosine squared. So now I'm integrating between 0. So my integral along C1 is just the integral from 0 to pi over 2 of cosine squared t dt. How do you integrate cosine squared t?
1/2 1 plus cos 2 angle.
Right, so you use the double angle formula, 1/2 1 plus cosine 2t dt. So that becomes 1/2 times t. What's the integral of cosine 2t? 1/2 sine 2t. That's between 0 and pi over 2. This becomes 1/2 times, plug in pi over 2, get pi over 2 here, plus plug in pi over 2 here, what happens? You get 0 because sine of pi, sine of any multiple of pi is 0, so that's going to be 0. Also, when we plug in zeros everywhere, you also get 0, so that's just, alright, that's just pi over 4. Now we're going to do C2. And for C2, our RT is going to be what? 0, comma?
1 plus
1 plus
2.
t. R prime just going to be 0, comma 1, which means the magnitude of R prime is again going to be 1. Hopefully I didn't emphasize it here, but maybe I should. Technically it's cosine t times 1 dt because of the magnitude. Just want to make sure that we didn't ignore that. So the magnitude is 1, and so for now I'm going to find f. This is going to be what?
0.
This is going to be 0. So 5, I'm actually going to be integrating from 0 to 2 of the function 0 squared times 1 dt, and that is 0. Definite integral of 0 is just 0.
Don't erase this, please.
Huh? What?
Don't erase this board,
When
please.
you go straight up, it's not a function. It's not a function. There's no
Why is it 0 to
When you go straight up,
0 to 1.
area, and integral just find the area of anything.
Okay, thanks.
Excuse me,
But in either way,
Professor.
it's going to be 0. Yeah?
Professor, why the parametrization here is cosine t sine t, right there is 0 to 1 plus t? I don't get it.
There are two pieces. One part is a circle. We know how to parameterize circles.
Okay, cosine t sine t. Right.
R cosine t, R sine t, where R is the radius.
Okay.
If there's a center, you add something to that. But we know how to parameterize this, so that's what we did here.
Okay.
Over here, we're parameterizing this.
Okay. So from 0 to.
So I do one integral for this part, which is
Okay.
here. Now I'm doing the other integral for this part, which is here.
So for the first part is 0 to nothing. So 0 to 0. 0 to. So 0 to. How do you get 1 plus t?
Log.
Okay, you have to go over the previous lectures. We already did this. If you want to go from x1, y1 to x2, y2, it's always going to be x1 plus x2 minus x1 times t, comma y1
Oh, yeah, yeah.
plus y2 minus y1 times t.
Okay.
You start at the first point,
Oh,
you
okay,
add something to
yeah.
get to the second point, then you start here, and then you add
One
something to get there,
plus-
and you attach t to the second point.
Okay.
Professor, assuming this to be true, can we just omit vertical lines from here on out in smoothwise functions?
No.
Okay.
Can you see why?
No.
Yeah?
So we're using this to find the area of the curve, right?
Yeah,
So,
which it doesn't have to be 0.
yeah, why would the 0 make sense? Like, why can the area be 0?
Well, look at your function. That's where the difference is. My function is x. What is the value of x's along the y-axis? It's always 0.
So there's no area.
So it's not like a vertical line will always give you 0. That's not the impression you should take away from this. The impression should be you're computing the height above this curve, which is actually given by the function that you're given. Okay? So it doesn't have to be 0 because it's a vertical line. Don't take that away.
Okay.
Because if this was y squared, then this would not be 0. This would be some function that we'd have to compute here. But in this case, it's x squared. So my x happens to be 0 along the y-axis, and that's why it's 0. It's also possible, depending on the function, my function could go above the xy plane and then go below the xy plane in such a way that everyone cancels out. It really depends on the function you're dealing with. So the intuition you might have from Calc 1 and 2 doesn't directly apply here. You should just use the definition. Just always go through these 5 steps. That's how we define it. Yeah.
Can I get a visualization of the x squared in this scenario? Like, what does it look like? That
The x squared would literally be
Is
the
it up
0
in,
function.
it's up in the z direction? Wait, what? I remember you drew where there was like the function is up above and the distance between the two is z, and
So you want to see a visualization of this? Which we're not always going to do this because it's kind of annoying to sketch. But what you should imagine here is we're in 3 space. There's one curve that's going from here to there in 3 space.
Yeah.
Where the height of that curve is x squared. So at the point where x is 1, the height of this curve is 1 squared. Once it gets to once you're over the x equals a half, the height is now a half squared, which is a quarter. So the function does this. By the time it hits here, it's 0. So the height of your fence is decreasing by a squared value until it hits 0 on the y-axis. And then it stays 0 this whole time because the height is given by the x-coordinate squared. Right? So you figure out along all these points, you're just computing the square of the x-coordinate, which it slowly is going to decrease to 0. Right? And then it stays 0 here. And that's because this guy, the height here, is given by the height is f, which is defined to be the square of the x-coordinate. Doesn't have to be that, but in this case, that's what it was. So you can know that something like that is happening, but it's not exactly important for you to visualize this part. You need to visualize this part in order to compute the integral. So then we have that.
Professor,
Yes.
so since you are computing the area, don't you, I know that in this case.
Well, we're not done. So let me actually finish this problem because the last step is just as important.
Where is 0 is where?
So finally, the integral along C, you have to remember, is the integral along C1 plus the integral along C2. You have to eventually add things up. So now this, from the first part, I believe you got pi over 4, plus from the second part, now we got 0. So it turns out the area of this thing is going to be pi over 4. Okay, so
Okay, yeah, this is the point.
any other questions?
So it's an integral over 0 squared. Because it's x squared, that's why you put 0 squared.
Yes. Okay. Another important factor. Sometimes you want to integrate with respect to x or y. And there are going to be some important integrals we're going to look at later, which is actually going to be a sum of integrals like this. But if we want to integrate with respect to x, this is the path we follow. So you can look at the integral of f of x, y with respect to x. So I'm integrating this with respect to the x coordinate. And so very similar definition. You're going to parameterize the curve, plug that parameterization into your function, that's giving you the height at the whatever point you're at. And your dx, like substitution, you know, if you set your x is equal to x of t, then your dx is going to be x prime of t dt. So this is going to be x prime of t dt. So instead of the magnitude of r prime, if you're integrating with respect to x only, you just put x prime here. And get f of x y dy, similar definition, it's f of x of t, y of t, times y prime of t. I'm avoid writing the dot, because there will be cases where we were doing a dot product, and I want to avoid the confusion. But there are multiplication.
So what would it say?
Huh?
What would the wording be when we have to switch from D, T, whatever to, yeah, when we have to switch from R to X, what's the wording going to say? Is it going to say like along the X axis? Like how are we going to know?
It's going to say this.
It'll just have a DX and that's it?
Exactly.
And then we're just supposed to just
Yeah.
show that.
Yeah. The
But it's
integral is
still
going
gonna say-
the integral is going to kill you. That's what I was talking about. The D whatever is going to tell you what you need to do. So we're gonna have D this, D that, they all mean something different.
But no, because it still has the, oh, okay, so it says DX and we're supposed to just put it to DT because in the other one it's DS.
DS.
So that means.
And by
R.
definition, remember your S was the integral of magnitude of R prime. Right? Which means if you
That's the
differentiate
arclength,
this, fundamental theorem of calculus says it becomes that. So that's why we swap ds out with this guy.
Mhm.
So yeah, the integral will tell you. The integral says do me with respect to x. Of course there are other reasons when, but it's not really going to come up in this class, but there are other reasons when you always have a goal to compute this integral, and you will know what your goal is. If you care about the length of the curve, or do you care about what the x-coordinate is. Right? It matters what you're doing. Right? But in terms of this class, how you know when to apply which formula, you have to read the integral, because the integral is going to tell you. Do it with respect to x, or do it with respect to s, or do it with respect to something else.
Professor, these examples don't be like the ones in the homework. I just wanted to point that out.
Which
These are very, elementary, and then in the homework,
we didn't have any homework problems like this yet. The homework problems we have was, what do we do? Like
I see the integrals in general.
I don't understand what you mean. I don't understand what you mean.
Quiz is what it is.
The problems with all of the weird limits and all of the weird shapes and stuff, that's what I'm talking about.
Okay, give me an example.
Like number 9, I didn't like that one on the homework.
What was number 9? I don't know.
I just know it went to 0.5 at some point and I didn't like it.
Even the tutors didn't know what to do with that. They didn't.
I went to the math center and they're like, I can't do this.
Yeah. That's not a lie. I'll quote Andy on that.
Okay. Let's do an example. Okay, so we're going to do the integral on c of x e to the y times x. C is the arc of the curve x equals e to the y from 1 equals 0 to e equals 1.
It's close connected.
Okay, tell me what you guys will do here.
So y is equal to 2.
So what do you want to do here? You want to parameterize? So what do you think of doing?
So x is equal to e to the t and y is equal to t.
Right. It's not a circle or a straight line, so we don't use the straight line formula. We don't use sine and cosine. We just parameterize in terms of one of the other variables. Here, since x is already a function of y, just let it parameterize in terms of y. Let y be t, and then x will be e to the t. What are the limits?
0 to 1.
0 to 1. Why?
The points? The y.
Well, literally why? because y is t. Right? Y equals t is what this is saying. And so my t values are really following my y values. And my y values here are 0 to 1. So we'd find r prime, which in this case is going to be e to the t,
1.
e to the t, 1. What do we actually need here, though?
Just the x.
Just the x, right? We care about the x. That's e to the t dt. And so now what are we going to do?
Can't find the magnitude.
We don't find the magnitude for this one. So now we're going to find the function. What does our function look like here? X is e to the t times, here my y is t, this is also e to the t, so it's e to the 2t. And so now we integrate. Just integral from 0 to 1 of e to the 2t times the derivative of this guy is e to the t to the t. So it's pretty much 0 to 1 of e to the 3t. So this is going to be equal to, what's the integral of e to the 3t? So that's going to be what?
1/3 e to the
Okay. So x is equal to t and y is t. Oh, okay.
That's that. Often, integrals with respect to x and y occur together. Something like integral along c, you're given some function p of x, y, dy, dx, plus some other function q of x, y, dy. Right? So something like that could happen. In which case, you do it one piece at a time. You parameterize this, you plug in the x prime here, and then you parameterize this, you plug in the y prime. And this in particular is a very important integral. We'll talk about this later on. It gives you something like work. But it's basically just doing two of these guys. Do you have an example?
Why do we not need the magnitude in this case?
Hmm?
Why do we not need the magnitude?
Because we're doing it with respect to x. It's a substitution. Right? Remember, if we have f ds versus f dx, right? So here, when you're doing dx, you're doing a substitution. You're swapping something up. So if you know your x is equal to x of t, your dx is going to be x prime of t dt, right? Using the substitution rule. So you're just going to plug this in.
Oh, okay.
Here we're doing ds, and we know that our s is the integral of the magnitude. So your ds is going to just be that guy dt. That's why this one has a magnitude, that one doesn't. It depends on what we're integrating with respect to. We have formulas for these guys. Right, S here represents arc length. Arc length we know is a magnitude. It's an integral of a magnitude.
Professor,
Yes.
can you do a similar example like this? One more example. Is it possible?
I'm going to do better. Let's do two at the same time. Let's do one like this. Right, integrals of this form are going to be very important, and they're actually going to show up in one of our fundamental theorems. Right, there's going to be something called Green's theorem, which is a very important kind of theorem, and it deals with integrals that look like this. So they're important for you to compute. For an example. Integral along C of y dx plus x squared dy where C is given by the following. Y equals 4x minus x squared from 2 comma 4 to 1 comma 3. So what's the first thing we're going to do? Parameterize. How are you going to parameterize this? Set x equals t, so my y is?
14 minus t squared.
Okay, and what are my limits here?
1 to 2. 0 to 0 to 1 to 2.
Is it gonna be different on both curves? On the x1, it'll go from 1 and 2, and from the y1, 3 and 4?
No. Remember where our limits come from. Our limits come from the parameterization. So whatever we do at the parameterization would apply to everything. It's all one curve. Both of these are being computed on one curve. Our parameterization and our limits come from the curve itself, not based on this. It goes from 2 to 1. Right, now there's a distinction between that. Direction actually matters here, and we'll talk a little bit more about when direction matters from when it doesn't. If this were a ds integral, it actually wouldn't matter whether I went from 1 to 2 or 2 to 3. But it'll matter here. In other words, this is my lower bound, that's my upper bound.
Well, can you tell us why?
Start to finish. The direction in which you're moving
Not the
matters.
x.
The x is decreasing.
Okay.
Right? If you put like 1 to 2, that says you're increasing from 1 to 2.
But how are we supposed to know that? Like, you just,
Because I'm telling you now.
but you're not gonna be telling us on the exam.
By the time you get to an exam, I would have told you everything you need to know for the exam.
Okay,
I'm not gonna give you an exam
I don't
on
know how you
this
found
now.
those limits. That's what I'm saying.
So you
From the coordinates.
So you just use the x you elected to use.
So
the
my x was t,
Mhm.
and so my t values and my x values are essentially the same.
Okay.
And so to figure out my t values, I'm going to look at my x values.
Okay.
And so I see here, I go from this to that, which means this is my initial point, that's my final point.
Okay.
Now, I'm going to talk about context in which direction matters from when it doesn't. But for now, just remember, when you're doing dx, the direction matters because it's not a magnitude. You're actually having the sign
but
will
when we
affect
flip it, can't we just change the sign? Or about, like, in the end?
You could, but I didn't. So this is part of what I'm saying. I haven't told you you could do that yet,
Oh, okay, alright.
but I will mention that at some point.
Gotcha.
But yes, you could just do your 1 to your 1 to 2 and then put a negative sign in front
Okay.
based on that. But I'll give you some rules for that in terms of when orientation matters and things like
Oh,
that.
so okay, I get it now. So okay, because you picked x equals to t, just take the limits from x equals to t.
Yeah,
You could have just said that.
I did say that. And we even said that last time. Remember when in the last question we had dy, and we had y equals t, and I told you y is at 0 to 1. And remember we went through that whole thing, and there's it's because the y coordinate. I did say that. So the limits do come from your parameterization, so you have to be careful how you're setting up that parameterization, because that's going to tell you. I'm going to transform this integral into a dt integral, so I need to follow my t, so I need to figure out what is t in the way I set this up. My t is just the x, and so I'm going to just look at the x guy. If my t was set up in terms of y, it's going to be the y guy. If my t was set up in terms of theta, I'm going to be looking at the angles, things of that sort. So it depends on how you're setting it up. Okay, so now our prime is going to be 1 comma 4 minus 2t. Now what I want you to take from that is that this guy means your x prime is 1 dt. This guy means your y prime is 4 minus 2t dt. Right, the r prime is going to tell you separately what your x prime and y prime are. We don't need the magnitude here, so we just go straight to figuring out what our function f is. Well, at this point we just swap
Excuse me,
it.
professor.
Yes.
Shouldn't the x prime? Oh, never mind.
Yeah, r prime is x prime comma y.
Okay, yeah.
So now we're actually just going to substitute things in. Right, so our limits go from 2 to 1. And I'm going to substitute the y. My y is this guy.
14 minus 2t.
Times my dx, which is 1. Right. Technically it's 1 dt, but I'm going to factor out all the dt's to the end. Plus, now I have my x squared. My x is just t, so this is t squared. Times my dy. My dy is going to be this guy. And so my integral along c is that integral. And how is that going to look? This is 4t minus t squared plus, I'm just going to distribute this, 4t squared minus 2t cubed. So this is 2 to 1 of 4t plus 3t squared minus 2t cubed.
equals,
Okay, so from here it's kind of annoying. It's really just doing top 1 again. So we're going to integrate that. That gives us 2t squared plus t cubed minus half t to the 4th between 1 and 2. So I'm going to plug in 1, 2 plus 1 is half, minus, going to plug in 2. So this will become what, 8? Plus 8, minus 2 to the 4th is 16 over 2. It's another 8. So these guys equal each other. And so what am I going to have? 3 minus 8 minus a half. Minus 5 minus a half. So that's minus 11 over 2.
so the area is negative.
Yeah, but this is not an area integral. Remember when we defined what makes an area integral? A ds integral is an area integral. And technically, area can be negative if the function is below the plane. Right? In that sense, the interpretation that we had in Calc 1 about negative area applies here. So it depends on what your function is doing and everything. But the meaning of an integral like this, what we did just now, the p dx plus q dy, the interpretation wouldn't really be an area. It has a different interpretation, which I'll talk about later. For now, I just want you guys to get the computations down, then we can talk about applications later. Yes?
What would that look like? Does that mean that it's going, like, it's projecting downwards, like on the V? Like it's going, like the opposite direction? Like the curve?
To see what this looks like, you'd really have to change your dimensions a lot.
Okay.
It's not going to, it doesn't really have a picture. If you want to kind of
Like what does that
imagine,
mean? The negative 1, 11, 2?
what you can think of is, this, and it's something I'll talk about later, but what was our curve? It was a parabola. So you can notice that what you can think of this, you can think of p dx plus q dy as something like this. PQ dot product with dx dy. Right? This guy here, we were talking about fields last time. This is going to describe some field that you're in. And this is representing the path that you're traveling within that field. So you can kind of interpret this in terms of the work. So a negative here kind of means you're losing energy as opposed to gaining energy. So it's kind of weird to put a picture on this. You can more think of it as walking uphill versus downhill and how much force you're exerting to do that. Right? So clearly here, based on the direction we're moving in our curve and the environment we're in, we're going to be losing energy to move from this point to that point. But again, that all comes later. Right now we're really focusing on the computations, the raw computations, and we'll kind of talk about applications in a bit. I mean, we will sort of get to that by the end of this section, I think, but it's still going to be a while before we get there. A couple things I want to mention here, and they're kind of related to Vanita's question, so we eventually got to it. This will kind of go without saying, but I think I'll mention it now, but in the future you kind of know it almost goes without saying. If it doesn't go without saying, I will mention it at that point, but for the most part, you can just kind of assume this moving forward. we right, so we're kind of doing this as our curve living in R2, but it is possible to do it when our curve lives in R3. So let's say we're in R3 and our curve is not stuck in the XY plane, but our curve can move out of the XY plane. In that case, the vector that describes your curve would have 3 components. But all the integrals I mentioned so far would have a similar definition. So in this case, your f ds would look like f of x of t, y of t, z of t, times the magnitude of x prime squared plus y prime squared plus z prime squared. Right, you can extend the definitions I gave you to include a third variable, and everything else would be fine, and the others are similar. Right, and you could even extend it beyond three variables if you want. So the definitions actually hold true. Once you expand the Riemann sums definition, it'll work out in higher dimensions. So we did things here where we only had the variables x and y, but it could extend to the variables z or other variables in the natural way. The definition just kind of expands to include more variables. And you can kind of do that without worrying about something breaks. The other thing I want you to note is orientation. Right? So this refers to the direction we are traversing or traveling along. And the notation here is we use negatives because it actually literally is a negative computation. So this means if C is a curve, then minus C denotes the same curve traversed in the opposite direction. So in that case, if you're visualizing moving from there to there, that's C. If you have exactly the same curve and you're going from there to there, we call this curve minus C. And that's notational, but when you're computing the integrals, it literally turns out that you put a minus sign on it. Another thing you should realize, orientation matters for dx and dy integrals. Because whether your x is increasing or decreasing, remember your integral here would depend on the slope, the x prime and the y prime. Clearly, if you're increasing or decreasing, the slope changes sign. So the x prime will follow the sign of what your x value is doing. So, so it matters for those, but it does not matter for integrals with respect to arclength. This means that if I have the integral along C of f dx, I can think of this as the negative integral along minus C of f dx. Those two I can think of equivalent. If I can travel in the reverse direction, but I just put a minus sign on the outside because my x prime will change signs. Similarly, if I have f dy, this is the negative of the minus C of f dy. But if I have integral along C of f ds, then that's exactly the same as minus c of f ds. The direction does not matter because it's respect to length, and it doesn't matter if I measure the length of this desk from this side to that side, or from this side to that side, it's going to be the same length. And you can also realize that because you're taking the radical of components squared, it's always going to be a positive number. It's not going to contribute a sign to your calculation. Yes?
How many points are you going to take off when I forget to change the sign?
Don't forget to change the sign. And a lot of times, and this is, to go to that point, that's the reason why I wanted you guys to think of it in terms of beginning to end, where you want to think of the integral as moving from the initial point to the final point. Because if you think of it that way, you actually don't have to remember to change the sign.
Okay.
Right? Because of how integrals work. The integral from a to b is actually the negative of b to a. So once you kind of let your integral do the talking, saying where you're starting, putting it at the bottom, and where you're ending, put it at the top, you don't have to literally remember to change the sign.
But you did all of them 5 steps right. You like us, you could just be like, all right, or you
No, I'm not going to.
No partial credit?
I mean, right now it looks very dry the way we're doing these computations, but these integrals, they can have really meaningful consequences, right? A negative sign versus a positive sign can have dire consequences happening, right? It's the difference between everything being okay and a bunch of people getting electrocuted. It's not. Because you apply this in electromagnetism and all sorts of dangerous fields.
Oh yeah, it's been in all of the physics classes. I get it, yeah.
Yeah, it's important. I'll see you guys on Thursday.